All right, for this video, I'm going to give you some examples of how to determine whether something is polar or nonpolar, and then we're going to go over interparticle forces as well. So the first thing you want to do to determine polarity is to actually draw the Lewis dot diagram. So for example, this one, we're going to put P in the middle, then we're going to spread it out with the hydrogens. You want to try to make it as symmetrical as possible. We know that these are bonded together, so we can go ahead and at least put a single bond between these. And then we just need to spread out the rest of the valence electrons. So first of all, P has 5 valence electrons to donate. Each hydrogen has 1, and there's 3 of them. So that gives us a total of 8 electrons to spread out among this picture. And if you look at the bonds, each bond represents 2 electrons, so we've used up 6 in the bonds, and phosphorus still needs 2 more. Hydrogen is stable with only 2. So hydrogen and helium, they only need 2 valence electrons. But the rest of them usually need 8. So we're going to put 2 more electrons on the phosphorus, and now we've used up all 8 of our electrons. So now we need to determine if this is polar or nonpolar. And what we're looking for is kind of the symmetry of the charge. So if all of the negative charges, all of the electrons are evenly distributed among the whole molecule, that's going to make it nonpolar. If there's one part of the molecule that's more charged than another, that makes it polar. So in this example, those 2 little electrons, the 2 dots on the P, are making that side of the molecule slightly more negative than the opposite side. So we say that this one is polar because of those electrons. There's nothing canceling out that negative charge, so it's kind of lopsided. All right, let's do another one. So for silicon dioxide, first you might want to go ahead and add up the electrons, silicon or valence electrons. Silicon has 4, each oxygen has 6, and there's 2 of them, so that makes it 12. So we're talking about 16 electrons. So put silicon in the middle, oxygen on each side, and then we can go ahead and start to pair them up, or to bond them up. So we've used up 4 electrons, we have 12 more to go. So let's just start putting some electrons around. That was 6. And now I've used up all 16 electrons. So 6 for each oxygen is 12, plus 4 for the bonds makes 16. But we have a problem because right now silicon only has 4 valence electrons because of the bonds, and it needs to have 8. So what we need to do is to take off some of the electrons on the oxygen and make oxygen share. And so now notice that the oxygen on the right still has 8 because we've got 4 in the bond plus 4 more that belong just to oxygen. And silicon now has 6, so we're getting closer, but we're going to go ahead and make it, the other oxygen is also going to donate some. And there's something called resonance that we'll talk about another time. So for now, just go ahead and try to make your picture look as symmetrical as possible. And so now just double check, we've used up all 16 valence electrons, and everybody has 8, so everybody is stable. So now we can look at the charge distribution. It looks like silicon has double bonds on both sides, and the oxygens are the same type of element, so the oxygens are pulling just as hard on either side of the silicon. And so even though the Si to O bond is polar, the entire molecule is nonpolar. It's kind of like if I was the Si and the oxygens are big professional football players pulling on my arms. If I only had one of the oxygens, that would be a polar bond because the football player is going to pull harder than I pull. But if you have another football player on the other side and they're both pulling, they kind of cancel each other out. So the charge gets distributed evenly, and so this one is nonpolar. All right, this next one, we're going to put C in the middle. We have hydrogens on 3 sides and fluorine on a 4th side. Fluorine has 7 valence electrons, 3 here and 4 here. So that's a total of 14 that we need to spread out. Carbon's already good, it has 8, each hydrogen is good, so we just need to give some more to the fluorine. So we've used up 2, 4, 6, 8, 10, 12, 14. So this is our picture. We don't need any kind of double bonds. Now we just need to analyze if this molecule is going to be completely balanced out. And it's not, because fluorine is the most electronegative element on the whole periodic table. So fluorine is pulling harder on all those electrons, all the bonds. It's pulling harder than the hydrogens, and so this side of the molecule ends up being slightly negative, which means the other side is slightly positive. And so this one is polar. So notice that the first one was polar because of those extra electrons. This number 3 is polar because they're not the same type of element pulling, and so the electronegativity difference is going to make it lopsided. All right, we've got one more. So carbon is 4, hydrogen is 1, oxygen is 6. That gives us, that should be a 2. It should be CH2O. And so that gives us 12 electrons. So we're going to put C in the middle. We've got 2 hydrogens and an oxygen. And when we bond them up, that uses up 6 of them. The hydrogens are good. They don't need any more. Let's go ahead and give some to the oxygen. And now I'm out of electrons. I've used up all 12, but carbon still does not have enough. So what I'm going to do is take 2 of them off of the oxygen and make them share. And so now the carbon is sharing with that oxygen. So now let's look and see about the polarity. So there's no extra dots on the C, but notice that oxygen is really electronegative compared to hydrogen. And so oxygen is pulling harder than hydrogen, and so the oxygen side of that molecule will be more negative. So this one will be polar as well. All right, let's take a few minutes and look at some intermolecular forces. So first of all, sometimes we call them intermolecular forces if we're talking about molecules, but a lot of times they'll call them interparticle forces because really we're talking about the force of attraction between particles, and sometimes those particles are not molecules. So interparticle force is a better way to talk about them. So I'm going to start with the weakest one. This is called dispersion. And this happens actually with all molecules and all particles, but we usually don't talk about it if some of the other types of intermolecular forces happen because it's really weak. So if another type of force happens, we're going to talk about the stronger force because that one we say is more significant. And so if there's nothing else to talk about, if you have no other forces of attraction, then you would talk about dispersion. So usually we talk about this only with nonpolar molecules because they have no other force of attraction. So if you look at these two molecules that I drew right next to the word dispersion, we see that they're both about the same in terms of color. So there's no side of the molecule that's more negative than another. So they don't really have charges because they're both nonpolar. And so the question is, why would they even stick together? And the answer is because electrons are always moving. And it's kind of like if you just picture a class of kindergartners and you tell them run around the classroom. For the most part, they'll be spread out, but just purely by chance, they might all end up by the door for a few seconds. And the same thing happens with electrons, that they kind of get lopsided just purely by chance. So let's say that this one got lopsided so that all the electrons ended up on this side of the molecule for just a few seconds, which means that this side is just a little bit positive. Then what happens is that it creates a polarity in the one next to it. So if you look at that molecule next to it, as soon as those electrons get lopsided on the right side of it, on the first one, all the electrons on the second molecule will swim away from it. They don't really swim, that's just kind of how I picture them. They're going to swim away from that negative charge because similar charges are repelling each other. And so that would make this slightly positive, and now you see we have slight charges that are opposites, and so they can be attracted. And so now there's going to be a slight attraction between those two molecules. Now that only happens for a split second because once the electrons get redistributed, that attraction is gone. But when we talk about a sample of something, there are so many particles in that sample that it's always happening somewhere in the sample. And that, like I said, is the weakest form of interparticle attractions. All right, let's look at the next one. The next one is called dipole-induced, and to induce means to make it happen. So we talked about inducing vomiting. If you swallow a poison, means they force you to throw up so that you get the poison out of your body. So this happens when you have a polar molecule next to a nonpolar molecule. So in order to do an example of this, you would have to have two different substances mixed together. So something that's polar and something that's nonpolar. And then it just does what we talked about in the last one. Notice there's a positive side on the right side of that first molecule, which means all the electrons on the second molecule, even though it's nonpolar, they're going to swim over to that positive because they're attracted to that positive that's right next to it. And then that makes a slight positive on this side. And now we have that opposite charges. We've got that negative from one and the positive on the other. And so now they're going to be slightly attracted. All right, the next one is called dipole-dipole. This happens between two polar molecules and makes a lot more sense because you see those opposite charges. So anytime you have two polar molecules next to each other, the positive side of one will be attracted to the negative side of the other. Now these are slight charges, so they're not as strong as if you had real charges because it's just a lopsidedness, I don't think that's a word, but a lopsidedness of the charge, you know what I mean, as the electrons get distributed unevenly. All right, the next one is hydrogen bonding. This one is really important. This gives a lot of molecules really special properties. It's the strongest of the intermolecular forces. It's not quite as strong as ionic, but it is super strong, and it's kind of like an extreme dipole-dipole. So what happens is I've got two water molecules here. They are both polar, so they have dipole-dipole interactions. They also have dispersion because everything has London. Sometimes they call it London dispersion, just by the way. But if you notice, this one is special because oxygen is one of the top three most electronegative elements. So fluorine is number 1, oxygen is number 2, and nitrogen is number 3. So these three elements are the most electronegative of all the elements on the periodic table, which means when they pull the electrons toward them, they're going to pull harder than most elements. So you get more of a negative charge on those on the side where you have those three, more than most elements. Then hydrogen is the least electronegative of the nonmetals. So hydrogen is going to be the most positive without being an actual extreme positive. So we've got an extreme negative and an extreme positive. And then there's a third condition right here. Hydrogen also has to be bonded to either oxygen, nitrogen, or fluorine so that the electrons in this bond right here are getting sucked away from the hydrogen to make it especially positive. So hydrogen is positive a lot by itself, but if it's bonded to oxygen, it makes it even more positive because all those electrons are being sucked away from the hydrogen by a really electronegative element. If all three of those happen, the hydrogen bond, watch what happens, the hydrogen bond is between hydrogen of one and the oxygen of a different molecule. So the green circle is not a hydrogen bond. That is a covalent bond between the oxygen and the hydrogen within the water molecule. But if you put two waters next to each other, the hydrogen of one and the oxygen of a different molecule, that is the hydrogen bond. It's not a bond, it's an interparticle force. So I don't know why they call it a bond, but it's just one of the intermolecular forces. And then the last one is if you have complete charges. So now instead of a partial positive, notice the other ones are in parentheses. That means it's a partial positive or a partial negative. Now we've got extreme positive and negative. So the dark red one has completely donated its electron to the negative one. So we get a complete positive and a complete negative. And that attraction, an ionic bond, is also an interparticle force. That is the strongest of the interparticle forces. So when we talk about separating things because like melting point and boiling point, these are the things we're going to compare to see what boils at the lowest temperature. There's also covalent bonds, which are even stronger than ionic, but a covalent bond, like when you boil water, you're not actually breaking the covalent bond between oxygen and hydrogen because that's super strong. What you're doing is you're separating one water from a different water, because when you boil water, you're not getting hydrogen gas and oxygen gas, you're getting water vapor. And so you're actually separating the interparticle forces. So these are the forces of attraction we talk about when we talk about properties, but just keep in mind that covalent is even stronger than ionic. And that is it for today. So make sure you do those progress checks. It's going to allow you to test if you can look at a compound and see what kind of force of attraction it's going to have between it.